Hi, guys. Welcome to our lecture on chemistry. Um, chemistry, I didn't do too well in chemistry when I was a high school student. It's really one of the toughest subjects that you're going to come across in high school. For 10 or 12 years so far, you've been taught that, you know, letters are in one place and numbers are in another place. And they really do kind of occupy different places in your brain. And in chemistry, you put the letters and numbers together, and you've got all kinds of fancy abstract words that are difficult to be connected to. So um, I eventually became a chemist, and I'm not trying to talk you into becoming a chemist, but I hope it's going to make me a good teacher for you in addressing the content. And chemistry is really hard to connect to just because it's so abstract. You know, this is a model of what they call the Bohr atom, and there's this nucleus with nuclear particles, the nucleus, and the proton and the neutrons, and then scooting around outside there, you see these other little quick moving objects that's supposed to be representing electrons, and they're moving in all kinds of different directions. Well, this is the model we use to try to understand basic chemistry, but it falls short at so many levels. So there's depths and depths and depths of levels of understanding, and I'm going to tell you some useful lies just to get you through the superficial aspects of chemistry, and just hang in there, and I'll do the best I can to help you understand this. So, Mr. Doherty, why are we studying chemistry if this is a biology class? And the answer is because all biology is based in chemistry. Um, chemists might say something smart alecky to you at college, like, well, biology is just a division of chemistry. And of course, physicists say to chemists, well, like, chemistry is derived from physics. But anyway, the chemistry of life is how living substances are organized and composed. It's the basic components, and we're going to learn about what makes up matter and how atoms form chemical bonds, and then how do those chemical bonds and the rules that allow them to form impact living systems. And got a nice another representation here of an atom called neon. And neon's one of the noble gases. It's noble because it's above everybody else. Um, the nobility, what's the nobility do when they see peasants in the fields? They ride by. Do they say hello and ask how they're doing? No, of course not. They don't interact with the peasantry. And the noble gases are all found on the far right-hand side of the periodic table. None of them interact with any other matter. And that's because at a certain level they're happy. They've become fulfilled, as it were, for atoms in terms of the number of electrons they have. And hopefully I help you to understand that as well. So anyway, remember that all matter is made up of atoms, and they have at the center, at the nucleus, we have these positively charged particles called protons, and then outside orbiting the nucleus are these negatively charged electrons, and everything that's alive is made up of matter, and of course matter has mass, and it takes up space, and we borrow the term atom from a guy named Democritus. That's right, he's an ancient Greek philosopher, and he wasn't just interested in, science. He was also interested in political systems. Democritus, yeah, what system did he come up with? And what Democritus' idea was, he said, if I had a piece of paper and I tore it in half, and then I took that half and I tore that in half, and I did that over and over and over again, eventually I'd get down to this piece of stuff I couldn't tear apart. He called those atomos. And so we've taken that term to represent the smallest unit of matter. And it's not really true. Atoms aren't indivisible. Atoms can be further divided into these things called subatomic particles, right? And so remember, we've got protons and neutrons in the nucleus. Protons are positively charged. Neutrons are neutral, and then those electrons are negatively charged, and they're really small. And those electrons can be found in this place called the electron cloud. They're moving at the speed of light, so it's hard to say where they're actually at. But I love this little animation at the bottom here to represent an electron cloud, right? And then the nucleus would be somewhere in the middle there. We can talk about these particles in terms of their charge and their mass. In fact, we say that a proton has a mass of 1 AMU. That's 1 atomic mass unit. Neutrons have no charge, and they're slightly more massive. They're 1.001 AMU. And then the electrons are negatively charged, but they have a really tiny mass of 0.001 AMU. And I want you to look at these three numbers, the three masses of the protons, neutrons, and electrons, and see if you can find any relationship. Is there a connection here? Protons are negatively charged. Protons are positively charged. Electrons are negatively charged. What would happen if I put two of those together? Well, anyway, the nucleus is the central part of the atom. It's composed of protons and neutrons, and those electrons are moving around in these discrete orbital shells at a discrete distance, and there's multiple orbital shells, and that's what we call the Bohr model. All right, this is the Bohr model of the atom. Those shells have specific names. Hey, if you haven't guessed it, look at the mass of a proton and a mass of an electron, and if you put a proton and an electron together, that would add up to 1.001 AMU, which is the mass of the neutron, it would also make it neutral. And so one way to think about neutrons is if they're simply a proton and an electron bashed together. Notice also that electrons, I've put this V sub c value here. That's the velocity of c, which is the speed of light. It's 3 times 10 to the 8 meters per second, which is really fast. That's 186,000 miles per second. 186,000 miles per second. You know, the moon's only about 275,000 miles away, so light could get to the moon in a couple seconds. And the Earth's only about 25,000 miles around, so life could go around the Earth 10 times in 1 second. It's fast, real fast. Anyway. Electrons occupy discrete orbital shells, and they have names. And since we're really only interested in the first part of the periodic table, that is the relatively small atoms, we're only going to be interested in the first couple of shells, and they have names. The name of the first shell is 1s. It's 1s because it's the first shell and it's spherical. S stands for spherical. The name of the second shell is 2s, and it's also spherical. You could be saying to yourself, wait a second, Mr. Doherty, it says 2sp here. And I'm going to bastardize the facts here just to make it a little bit easier. There's a 2s shell, but we're going to say there's a 2sp shell. And it's the second shell. It can hold 8 electrons. The first shell is filled with 2 electrons. There's a 3sp orbital shell as well. Well, there's actually a 3s and a 3p orbital shell. It doesn't matter too much, but the third shell is going to be filled with 8 electrons as well. And I've got an activity for you to do some counting with these things. And it's important for you to be able to do this accurately. All right, so I have a whole other demo video for you to work on that activity next. And it's really important in helping you understand it. But really, you know, if you're not a physicist, you don't really care about what's going on in the nucleus. You really care about what's happening in these electron orbital shells, all right? Because atoms want to have their outermost shell filled, okay? So you can see helium here. It's at the top. Its atomic number is 1. It's got 1 electron. Is it happy? Answer is no, because, up top we've got hydrogen, not helium. And it's not happy because it only has 1 electron, and that First orbital shell needs 2 electrons to be filled and happy. Now, helium in the middle is happy. Helium's one of those noble gases. Helium doesn't need to interact with anybody. It doesn't form chemical bonds readily, and it's because it doesn't really need any electrons. Down the bottom, we see carbon here, and you see carbon's got 4 electrons in its outer shell, and that's going to give us some ideas about what kind of bonds carbon likes to make as well. All right, so there you go, protons, neutrons, and electrons. Is that it? Well, no. Can I break protons, neutrons, and electrons into other particles? The answer is yeah. Yeah, you can. In fact, protons, neutrons, and electrons, a bunch of other stuff are made up of these fundamental particles, the fundamental particles. So the fundamental particles come into categories called hadrons and leptons, and there's these quarks, and the quarks can be up or down or strange or charmed. And then can I break up, so for instance, a proton's made up of 2 up quarks and a down quark. Could I break up these quarks, Mr. Doherty? The answer is yeah. There's a whole theory called string theory. But of course, we're not here to learn about string theory. You know, like how small can I go? The answer is Planck's constant says that the smallest thing you can find in this universe is 10 to the negative 35 meters in length, which is really small. So, boom, mind blown. Think about Planck's constant for a minute, and I'll see you on the other side.